Hi, everybody. Welcome to our session on how embedded TCP/IP stacks breed critical vulnerabilities. I'm Daniel Dos Santos, a research manager at Forescout, and today I'm joined by Stanislav Dashevsky, a security researcher at Forescout. We would also like to thank our co-authors, Jos Vetsels and Amin Amri, for the work. And we would like to say that at Forescout Research Labs, we analyze the security implications of hyperconnectivity and IT-OT convergence and other trends such as IoT emergence in enterprise networks. Today, we'll be talking about Project Memoria, which is a large-scale study of TCP/IP stack vulnerabilities. We'll then drill down into Amnesia 33, which is our first study published under Project Memoria that deals with vulnerabilities in open source TCP/IP stacks. We'll do an analysis of these vulnerabilities, talk about the consequences of these vulnerabilities, and then finally discuss a little bit what comes next in our research. So let's talk about Project Memoria. So the goal of Project Memoria is to have a large study of embedded TCP/IP stack security. We want to understand why they're vulnerable, how they're vulnerable, and what we can do about it. The idea is to have a quantitative and qualitative study so that we not only look at security vulnerabilities across many stacks, but we drill down into components that are more prone to vulnerabilities to understand also the exploitability and other nuances of vulnerabilities in TCP/IP stacks. This project will be done by Forescout Research Labs and other collaborators. And we would like to say that the motivation behind this project is that we used to see several vulnerabilities in TCP/IP stacks, especially in general purpose TCP/IP stacks in the late 90s and early 2000s. You can think of things like the ping of death, wing nuke vulnerabilities affecting Windows, Linux, and so on. But nowadays, we see this rise of embedded devices and the IoT world, and just scaling up to billions of devices nowadays. And we see that TCP/IP stack vulnerabilities are making a resurgence because they are used across many of these devices. We saw in the past 2 years research such as Ripple 20 and Urgent 11 that highlighted this risk. And to start talking a little bit about this kind of risk, we need to understand a bit about the embedded systems supply chain, right? So embedded devices and IoT devices have several hardware and software components that are basically produced by different vendors and mixed and matched to form a device that ends up in an enterprise network. And we have components such as microcontroller units, systems on a chip. We have connectivity components. We have applications such as library, daemons, platforms, and so on. And at several steps in this supply chain, there might be a TCP/IP stack that is introduced in a device, right? So one of the reasons why looking into TCP/IP stacks is interesting is because of this need to understand where they are in a device and how a vulnerability in one TCP/IP stack high up in the device in a supply chain ends up trickling down into devices. But there are other reasons why we want to target protocol stacks. So I already mentioned the wide deployment, right? And the fact that vulnerabilities trickle down to many vendors, but also the fact that there is an absence of a software bill of materials, so that vulnerabilities that are fixed in a core stack might just never make it to all and firmer because of not just the supply chain being long, but also sometimes being obscure. There is, in TCP/IP stacks, there's always a good chance of finding exploitable bugs because they tend to be written in low-level code, in memory unsafe languages such as C and C++. They are often old code bases that were written several decades ago, and they involve complex parsing and state machines and so on, which are difficult to get right. Not just finding exploitable bugs is easier, but it's interesting that they are also often externally exposed components. They often run as privileged and low-level components when there is an operating system. Sometimes there isn't even an operating system and the stack runs on a flat memory model. So basically, these patching issues plus the long lifespans of the devices that are affected by these kinds of vulnerabilities and the broad trickle down that we mentioned above lead to a high vulnerability lifespan, a difficulty in eradicating these vulnerabilities, which ultimately translate to a high attacker return on investment. And now to drill down into the details of Amnesia 33, I would like to give the floor to Stanislav.
Hello, everyone. Thank you very much for joining. My name is Stanislav, and I will tell you more about the Amnesia 33 study. Amnesia 33 is a study of vulnerabilities in open source TCP/IP stacks. It is a large-scale study of TCP/IP stacks. We analyze the security implications of vulnerabilities in open source TCP/IP stacks. We do an analysis of this study, and then finally discuss a little bit what comes next in our research. So let's talk about Project Memoria. So the goal of Project Memoria is to have a large study of embedded TCP/IP stacks security. We want to understand why they're vulnerable, how they're vulnerable, and what we can do about it. The idea is to have a quantitative and qualitative study so that we not only look at security vulnerabilities across many of these devices, but also the fact that there is an absence of a software bill of materials, so that vulnerabilities that are fixed in a core stack might just never make it to all and firmer because of not just the supply chain being long, but also sometimes being obscure. There is, in TCP/IP stacks, there's always a good chance of finding exploitable bugs because As Daniel mentioned, the TCP/IP stacks are the key for the connectivity of embedded systems and different IoT devices. But there are still quite a lot of popular implementations of these TCP/IP stacks that were not previously examined. For example, Microsoft's NetX, niche stack, and the Nucleus Net supported by Siemens. Therefore, I would like to present to you our first study into this topic called Amnesia 33. The study aims specifically at open source TCP/IP stacks, and we chose to explore open source targets in particular because, for example, according to this 2019 embedded market study, most of the embedded projects reuse the source code, which also includes open source, and a bit more than half of these projects are using open source real-time operating systems, and these are typically bundled with an open source implementation of a TCP/IP stack. And also, despite this growth in popularity, the security and privacy in these projects will still remain as an afterthought. We have broken down the research activities on Amnesia into several phases, and I will use them as my outline for the rest of this talk. I will now explain each phase in more detail to you. We started with the analysis of the existing vulnerabilities in different stacks, and we also studied related write-ups and research reports. As we immediately noticed, apart from some of the recent studies, there are not so many vulnerabilities disclosed for TCP/IP stacks, even for very popular stacks used for decades. And while one might think that this is simply because these stacks are robust, it could also indicate the lack of public security assessment. So we started also with studying prior vulnerabilities in more detail, and we were inspired by the taxonomy of anti-patterns introduced in the paper called The Seven Turrets of Babel, which was written by Falcon Mohammed and his colleagues. Some of these anti-patterns directly apply to the historical vulnerabilities we have seen in TCP/IP stacks. And for example, some of them are permissive parsing when there's no validation of the data that is coming from a network packet. There is also a variant of this called shotgun parsing when the processing validation code is mixed together and instead of doing validation first and then processing second. Also, more generally, there was a general absence of bounds checks, and also we saw that there were a lot of integer wraparound issues, and there was also quite some number of state confusion bugs, like the absence of proper request and reply matching. Another interesting pointer for us was the fact that they may be unclear and conflicting design documentation that has been used to develop these TCP/IP stacks, and also that describe various protocols. These documents are called the RFC documents, and for instance, the TCP urgent pointer that was not properly defined in one of these RFCs has been already the source of implementation errors in the past. To select the appropriate targets for our study, we focus on stacks that have been used by popular real-time operating systems, and we also consider the potential numbers of devices that are using a stack that we could find online. To briefly introduce you to these stacks, we started with LWIP, that is very popular, and it's also a part of FreeRTOS operating system, and also it has been used in many other embedded projects. The micro-IP stack is also developed by the same author that developed LWIP initially, and it was designed to be even lighter than LWIP. Currently, it is a part of the Contiki OS project, and it is a quite popular base for commercial and non-commercial forks. The NatNet TCP/IP stack is currently used by the NatOS, and is also in active development now. And also the rest of the stacks mentioned here are the commercial stacks made public some years ago, and they remain quite popular to this day. We know that other researchers looked at some of them in the past, and these stacks have been found, has been around for a very long time, but this actually implies that there could be many versions of these stacks running on different devices that are considered end of life by vendors, especially if they're running some old versions. For looking for the vulnerabilities in these stacks, we use the combination of dynamic and static analysis. We first set up a fuzzing infrastructure using the libfuzzer tool, and we used white box code coverage metric as our guide. We could actually find a number of vulnerabilities in this way. However, there were some complications in setting it up for more embedded for some of the embedded targets. Moreover, it might be quite challenging to achieve the full testing coverage with this approach, simply because when the fuzzer is used out of the box, it might be not as efficient. And the reason for that is that some protocols require stateful fuzzing, and they also need more advanced means for computing checksum and passing through them. We also used a static analysis tool called Yorn, developed initially by Fabian Yamaguchi, and we would like to thank Gabriele Acerbi, who helped us to set it up. For this, specifically, we encoded some of the anti-patterns I mentioned earlier in the form of cold search queries. And still, as with any static analysis tool, there were sometimes high false positive rates because some of the vulnerabilities in TCP IP stacks are quite implementation specific, and they need to be adjusted for that. Finally, we also performed a lot of manual code inspections to explore the points of interest that we haven't covered with any of these tools before. So I would like to continue with first the positive results. For example, we could not find any vulnerabilities in 3 of our targets, which are LWIP, Cyclone TCP, and Micro-C. These stacks in general did not exhibit any problematic code anti-patterns that we have been looking for. And for example, they have the proper bound checks in place, and usually they in general have quite robust parsing code. We also found that these stacks are actively developed and supported, and when, for example, we contacted these projects for some other issues, they were quite responsive. 4 stacks, however, from the ones that we analyzed, were vulnerable according to our assessment, and in total we found 33 vulnerabilities with the top affected components that are DNS, IPv6 and IPv4, TCP and ICMP. The potential impact of these vulnerabilities ranges from different kinds of denial of service to information leak and remote code execution. We also found a few state confusion bugs like DNS cache poisoning. Now I will provide some more detailed analysis of our findings. Here I would like to show you how the amnesia vulnerabilities compare to the previous studies, and on the picture you can see the ratios between our findings and the previous work done by other researchers. It is worth to mention that we found quite a few vulnerabilities in the transport and the network layers, and these vulnerabilities are specifically interesting because most of them are independent of a user application that runs on top of them, and also target device that is vulnerable doesn't need to have any open pores for triggering these vulnerabilities. At the same time, it seems that the overall complexity of a protocol remains a good indicator of potential vulnerabilities. Here you can see that we found quite a lot of vulnerabilities in DNS applications. If we break our findings down by vulnerability types, we mostly get the following ones. So we start with the out-of-bounds read and write, where attackers control length and offset fields of network packets. And these offsets might influence memory-related operations. Then it follows by quite a number of integer overflows where different network packets are incorporated into assignments and comparison arithmetic. And there is also some number of state confusion bugs. And these bugs are not related to memory issues directly, but they can facilitate the exploitation of other issues in the stacks. Next, I would like to make just a few examples of the vulnerabilities that we have found in this work. On this slide, you can see the bytes that correspond to ICMPv6 echo request and the corresponding reply packet. Specifically here, I highlighted the ICMP headers that start from the hex value of 80 for echo request, and 81 is for the reply. Then there is a code byte, 2 bytes checksum, 2 identifier bytes, and the 2 bytes that represent the sequence number. While these 8 bytes are the minimum amount of bytes that an ICMP payload should have, which is exactly the header, some TCP IP stacks that we analyzed will interpret any sequence of byte that starts with 80, and they will think it's an echo request. So, for instance, the way they implement that is that when processing a request and preparing a reply, they just change the first byte of the header and the checksum in the ICMP payload, and then they just send the rest of the packet back. Here is an example of one of the vulnerable implementations, and it's the Pico TCP IP stack. This is the function that will take an ICMP echo request packet and prepare a reply that will be sent later on. On the line 68, the memory for the reply packet is allocated, and it will be the size of the data sent in the echo packet. Some properties of the echo packet are copied over into reply the next lines, and on the line 84, the data payload of the echo message will be copied into the reply using the memcopy function. Here it is explicitly assumed that the minimum size of an echo message is at least 8 bytes. You can see this quite lengthy constant in the third argument of the memcopy call. But unfortunately, there are no checks to validate that. So if we send an echo message that has only a header, and for example, it consists only of 3 bytes, the arithmetic operation in the memcopy call will overflow, and the size of the copy will become a large positive value. Therefore, in this way, when executing the memcopy operation, we'll attempt to copy more bytes into reply than we have actually allocated previously, and therefore we will write out of bounds. Next, I'd like to demonstrate some of the vulnerability anti-patterns that we haven't seen in the prior work, and they are more implementation specific and are related to parsing IPv6 extension headers and processing domain names in DNS packets. In the case of extension headers, we saw that their lengths and also the length of options within them might be not validated. And for DNS packets, we saw issues with not checking the length of a domain name, as well as not checking whether it was properly null terminated. The next example that I would like to show to you is about the destination options extension header, which is an IPv6 header used for setting packet delivery parameters. It consists of the next header, the header extension length fields, and a variable length field that is called options. And the options field itself consists of type, length, and the data fields. In general, IPv6 packets can have combinations of different extension headers with different kinds of options that you can nest into them. And here on this picture below, you can see the generic structure of these headers. Here on this slide, it's vulnerable function from Pico TCP, and the purpose of the function is to parse the destination options extension header and the nested options. So the function first sets a pointer to the first byte of the first option found in the header, and then it gets the total length of the extension header itself. Next, the function parses every option in the loop until it reaches the end of the options. Here in the line 9, it reads the length of an individual option before it iterates. And at the end of each iteration, the parsing loop jumps over to the next option using the length byte of the previous option as an offset. There are several problems with this implementation, and the first one is that the attackers may control the length of an individual option because it is just set in the header and it's not validated. Because of that, they explicitly and implicitly control the variable that holds the total length of the header. And with that, they can implicitly control the pointer that jumps over the different options within the header. So with this degree of control, attackers can either shift the option pointer to some unmet memory by providing large values to option length, or alternatively, they can make this loop to iterate infinitely by making the length of one of the options to be 0, and they can do that through the integer overflow that can happen during the assignment at line 9. The final example I'd like to show is a vulnerable function from the .NET, and this function has some issues with parsing DNS domain names. First, I would like to briefly illustrate to you how a DNS response record looks like. You can see it on the left upper corner of this slide. So this record contains a sequence of bytes that corresponds to a domain name that has been requested, and it follows with the domain type, class, time to live, and the resource data length bytes. And then there are the bytes that correspond to the resource data. For example, it could be an IP address that corresponds to the domain name in question. A domain name itself is a byte sequence that consists of domain labels, where each label starts with a byte that indicates the length of a label, and then it is followed by the label characters. A domain name also must end with a node byte explicitly that indicates where it actually ends. On the right, you can see the vulnerable function from .NET, as I mentioned, and this function parses individual domain names from a DNS response packet, and it tries to combine two things. So first, it returns the total length of the parsed domain name, which is then used by some other functions as an offset. And it also copies the domain name itself that it parses into a separate buffer that it allocates in this function. Before parsing the name, the function will first deallocate the domain name buffer if it contains some previously allocated domain name. And then it will allocate space for the new name based on the domain name length provided in the packet. The total length of the domain name is obtained by using the astrlen function on the line 182, as you can see. The code will then iterate over individual labels and copy their contents into the allocated buffer byte by byte. The problem here is that the astrlen function explicitly assumes that a sequence of characters is null terminated, and there are no checks whether the combined lengths of individual labels correspond to the length of the domain name. This allows attackers to explicitly control the allocation of the buffer. For example, they might set the null byte at a particular offset within a DNS packet. And at the same time, the attackers may control how many bytes will be written into it. So they can specify arbitrary label length and do that via these offsets. This is essentially a classical heap buffer overflow. For example, here on the left, you can see that the label length byte that says the label is 176 bytes long. We inserted here, however, a fake null byte that is about only 80 bytes. This means that we will attempt to write 176 bytes into the buffer that is just 80 bytes long. We managed to exploit this vulnerability by creating a malicious DNS server that replies to the requests from a vulnerable .NET DNS client. In this example, malicious DNS response contains two answer records. Here I would like just to provide a high-level overview, and the detailed exploitation write-up will be coming soon. The specifics are that the NatOS has a single heap allocator, which maintains singly linked free chunk list, and it has a deterministic best fit algorithm. Moreover, there are some very simple optional heap guards. So basically, it will just surround the heap metadata of an allocated chunk with the deadbeef bytes. It is therefore possible to shape the heap in a certain way. And we will first set the domain name of the first DNS answer that we send to a certain size to ensure that it is allocated at a certain position on the heap. Then the data of the first response is also set to a certain size so that we can allocate it right after the first domain name. And there also, after these two allocated chunks, there should be a free chunk in the memory. The domain name in the second answer record will be actually the malicious one, and we set it to the same size of the first domain name. So that the memory allocation algorithm allocates the second name in the same chunk where the first one was allocated. The bytes we provide in the second name will actually cause an overflow, so then we overwrite the next couple of chunks, corrupting the metadata of the free chunk as well. And this will currently work because there are no memory protections on the target that we were using. And in this way, we overwrite the pointer to the next free chunk so that it points to a local variable on the stack, which we would like to use on an offset for writing. When the chunk that will hold the data for the second answer gets allocated, the next pointer of the free chunk already points somewhere into the stack frame. And this is where the newly allocated data will be actually written. Therefore, whatever we specify in the data of the second answer will be written into that stack frame offset. And it will allow us eventually to hijack the control flow. So in this way, we can also then create the ROP chain and then redirect the execution to the shellcode of our choice. Here we have developed this proof of concept against the latest version of the NatOS, and for that we used the Ethernet 5 development board. As you can see here, the payload simply prints a string over UART, but we can do much more, like manipulating inputs and outputs. We can extract cryptographic key material or interact with other buses available on the device. The main lesson learned actually after this was that for embedded systems, there is a big difference between the perceived potential impact of a vulnerability and the actual impact and exploitability against a particular target. There are many moving parts that can actually dramatically change these factors, and I would like to mention some of them. The first one is the configuration of the stack itself. Because some components and features may be disabled, network buffers that we are trying to overflow may have different sizes on different devices. And also they might be using different memory allocators and so on. The network and hardware drivers configuration also play a significant role because some of the stacks may be configured to offload validation and filtering of network packets to them. Also, the target platform on which the TCP IP stack runs has a significant impact. So the things like memory protection support, whether it's enabled or disabled, different built-in security features, or a specific way in which the faults are handled within the device. Also, the presence of watchdog timers plays quite a big role in this. There's also a big difference between cases when a TCP IP stack runs as a part of real-time operating system or it runs just on a bare metal setup. To quickly illustrate these points, I'd like to show you two small examples. The potential impact of the vulnerability on the left is denial of service that can be triggered when reading out of bounds within the checksum calculation function. But to actually achieve this impact, the target device must not offload the checksum calculation to any other driver. Exactly this function must be called. Memory protection unit here must be also enabled, and it also depends on how the memory-related faults are handled. For example, in some ways it might just hang indefinitely, or the device can be reset after a while. The example on the right is a vulnerability that can lead to an infinite loop when parsing malformed TCP options. In this case, depending on a task scheduler, the entire system may hang, causing a denial of service. And if no watchdog timer is present, the system will hang indefinitely. Otherwise, if there is a watchdog timer, however, only the network functionality might be affected by the exploitation, and the system itself might be reset after some time. Thank you very much, and I would like to give floor to Daniel.
So thank you, Stanislav, for giving us so many details into the vulnerabilities that we found and insights into vulnerabilities in TCP/IP stacks in general. But now I would like to talk about the consequences of these types of vulnerabilities. So the first challenge that we have with TCP/IP stack vulnerabilities is to identify affected systems. In this research, we used 3 data sources, including documentation of devices that we found online instances of devices using tools such as Shodan, and fingerprints on proprietary repository, which we call the device cloud within Forescout. That allowed us to identify close to 150 potentially affected vendors. And these vendors produce devices such as embedded components, systems on a chip, connectivity modules, and so on, and network and office devices such as printers, routers, consumer IoT devices such as smart plugs and sensors, and OT devices that are used in building automation sensors and building automation systems and industrial control systems. Many of these vulnerabilities affect these components that are high up in the supply chain, such as the SoCs that we mentioned, and then trickle down to many different vendors and verticals, right? So that's why it's difficult to identify the end devices that are actually affected. We know that popular components and devices such as the Wi-Fi, SOCs, network switches are shipped in the millions, but other devices such as RTUs and OT devices are much harder to estimate. So it's difficult to know the actual number of devices that are out there. Another issue with TCP/IP stack vulnerabilities is actual patching, right? So for instance, we identified vulnerabilities on a TCP/IP stack that is produced and maintained by a vendor A, but that ends up in an operating system that is produced by another vendor and then embedded into a network management card of another vendor. And then finally, that is part of a UPS that is sold to an end user by a fourth vendor. And the vulnerabilities that were identified in the TCP/IP stack were never actually patched in the UPS because basically the operating system vendor is now out of business. So there is a broken link in the supply chain, which means that the end user will not get the proper patches for these vulnerabilities. So this is just an example that highlights a broader issue, which is the fact that vulnerable code spreads widely, especially in open source projects that we dealt with for Amnesia 33. Many of those start by forking code and then evolve independently. Sometimes only single components of another project are used. And then different versions of the stack might be forked into different projects. So we have a tree there that shows the example of micro IP, which is used by operating systems such as Contiki and NetAx and other projects such as OpenISCSI and some D-Link firmware. But the fact is that different versions of them are vulnerable in different ways, and the fixes are also being done differently. And that's what I want to discuss in this slide is who is actually responsible for fixes, right? We disclosed these vulnerabilities to coordinating agencies such as the CERT-CC and ICS CERT. They got the help of other security teams and agencies and so on. But despite all this effort, no official patches were produced for some of the original projects such as MicroIP and Contiki, which led to vendors implementing their own patches, which means that there's more code fragmentation and that all of these issues will need to trickle down to OEMs, product vendors, and end users, which, as we saw in the previous slide, is not always an easy task. But not just identifying and patching these devices is complicated, but there is also the aggravating factor that there are new attack scenarios that are enabled by these types of vulnerabilities, right? So nowadays there's this wide range of devices that are vulnerable, and several of them communicate externally. For instance, with DNS servers, we saw how DNS is an error-prone component that is of high value for attackers. And this basically means that several locations within an organization, now here we illustrate retail branch, enterprise HQ, and substation are vulnerable, right? And it might be that an attacker uses the DNS vulnerabilities for initial access and moves laterally from one part of the organization to the next, and in the end causes an impact in his or her final target. All of that using vulnerabilities in TCP/IP stacks. So the key takeaways from this research are that TCP/IP stacks are vulnerable across the board. There are some resilient stacks, but the rule of thumb is that we find many bugs upon a close inspection. These vulnerabilities arise from well-known bad software development practices. There are bugs in several components, but they tend to correlate with protocol complexity. The IoT risk management is very difficult because these vulnerabilities affect hundreds of vendors and millions of devices. The exploitability is highly device specific, and these complex supply chains make it challenging to determine, so to identify vulnerable devices and to patch and eradicate those vulnerabilities. But there is something that can be done on a more hopeful tone. We all know that it's difficult to identify the devices on the network that are vulnerable because that requires some specific knowledge, some accurate fingerprinting, and that patching sometimes may be impossible because the vendors may not know or not patch or even be out of business. But there are some specific recommendations that can be done to mitigate these issues, right? So disabling or blocking IPv6 traffic when it's not needed, for instance, because as we saw, several IPv6 implementations are vulnerable. And often they're not used within enterprise networks, so there's no reason why this traffic should be allowed. Relying on internal DNS servers for critical devices, monitoring the network for anomalous packets, and basically segmenting the network to avoid that critical devices are used as an early entry point, as the target of an attack, or even as a pivot point within the network for lateral movement. But we also want to talk about what comes next in this research and what we want to do in the future. So we see vulnerabilities resulting from protocol complexity and external dependencies in multiple stacks. We already have vulnerabilities in 6 stacks from one case of this type of vulnerability, and we have CVEs in 8 stacks for another case of this type of vulnerability. Both cases are reminiscent of issues seen in the 90s and early 2000s. We also see vulnerabilities in popular closed source stacks that are used in several critical devices. We already have 8 CVEs for 2 stacks there. And we just see that popular stacks tend to be highly vulnerable, non-robust, and non-RFC compliant. And we basically are going through proper and coordinated vulnerability disclosure for all of those issues, and we want to present them as soon as possible. We also would like to discuss the current disclosure process and how to scale it to the IoT supply chain, because as we saw, that's really challenging nowadays. And we would like to expand on recommendations about mitigation for other stacks or for other issues that we find in the future. And that's it. Thank you so much for listening to us. And I would like to take some questions. Thank you very much.